Up until now, the parameter t was chosen to represent a curve either out of convenience or because it represented time. Now we want to introduce a natural parameter that's called the arc length of the curve. So let's see what it means for a curve to be parameterized by an arc length. Let's look at two different representations of the same curve. Both of these representations, r equal cosine t sine t and r equal cosine 2t sine 2t, both draw the circle, the unit circle. Now, in the first example, to get the complete unit circle, the values for t must be from 0 to 2 pi. In the second one, because each of these trig functions have a period 2 pi over 2, which is just pi, we only need t values from 0 to pi. So both draw the same exact curve, but the parameterizations are different. Now in the first example, let's look at what the value of t is and the value of the arc length at that given time. So let's say we start at t equal to 0, and at t equal to 0, this parameterization, we have the vector cosine of 0, which is 1, sine of 0, which is 0. So we begin at the point 1, 0. That's when time equal to 0. Well, at that point, the arc length is also 0, since we haven't measured any distance on the curve. Now let's look at t equal pi over 2. When t equal pi over 2 in this parameterization, we'll have r equal cosine of pi over 2, which is 0, sine of pi over 2, which is 1. So we're at the point 0, 1, or this r is actually the vector pointing to the point 0, 1. Now at that given point in time, the t value was pi over 2, but what was the arc length? Now I'm assuming the arc length is measured from the start, so measuring this distance from where t was 0 to t's pi over 2. Well, to figure out that distance, it's just a fourth of the circumference of a unit circle, circle radius 1. So circumference of a circle is 2 times pi times the radius, which is 1 in this case. So a fourth of that circumference would be pi over 2, which is the same as the t value. So the arc length is actually pi over 2. Well, continuing around the circle, let's look over when the t value is pi. When t is pi, the r values, the vector, would be cosine of pi, which is -1, and sine of pi, which is 0. So we're looking at the point -1, 0 here. What is the s value, the arc length from the beginning, t equals 0, to where t is equal to pi? Well, the arc length will be this entire distance, which is half of the circumference of the circle. So the arc length here is half of the circumference, which will just be pi, the same as the parameter. At each value here, if we were looking at pi over 4, the t value would be pi over 4, and we would be having the arc length, which was an eighth of the value of the circumference, which would also be pi over 4. The t, the parameter t, is the arc length. So this curve is parameterized by the arc length. Now that just means that the parameter t is the same as the length of the arc measured from the beginning t value. So now let's look at this second parameterization. If t is equal to 0, we have that r equal to cosine of 0, which is 1, sine of 0, which is 0. So again, we're at the point 1, 0. The arc length at that point is also 0. Now measuring counterclockwise, let's look at t equal pi over 2. Actually, when t is equal to pi over 4, the value of r is cosine of pi over 2, which is 0, sine of pi over 2, 1. So the value of t is pi over 4 when we're at the point 0, 1. Now, what is the arc length? Well, the arc length's a fourth of the circumference of the circle, so the arc length is pi over 2. So notice the value of t, the parameter in this description of the curve, is not the same as the arc length. Continuing on, over here, we see that the arc length would actually be pi, which is half of the circumference, but the t value was actually pi over 2 to get that same value, and that's when we're at this point, negative 1, 0, or the vector negative 1, 0 is the vector from the origin pointing to it. So because the values of t only need to go from 0 to pi to draw this entire unit circle, then half of the unit circle is drawn at t equal pi over 2, which, notice the parameter t is not the same as the arc length. In fact, the parameter t is always half of the arc length. So this curve description is not parameterized by the arc length because the value t is not the same as the arc length. Now let's get a formula for the arc length, and we want that formula for the arc length as a function of time. So, or function of whatever our parameter t is describing the curve. So let's r of t describe a smooth curve, and t is greater than or equal to some value a. So that's the initial t value. The arc length given by this function. Now, if you remember in the last section, we had that the arc length from 0 to some value of t was just the magnitude of that velocity function, or the speed. So let's say that, okay, so if r of t is equal to x of t, y of t, z of t, then r prime of t is the square root of x prime squared plus y prime squared plus z prime squared. Now, if I'm going to find a formula for the arc length in terms of the parameter s of t, that means that I'm going to have this upper value variable. So what I need to do when I'm writing my integrand is I can't use that same variable. I need a dummy variable, just something different than the variable that's up in the limit. So I'm going to use in this description. So r prime of u will be, actually I wrote the magnitude, I'll just change that. The magnitude of r prime of u will be the square root of x prime of u squared plus y prime of u squared plus z prime of u squared. So the integrand, and this is just from the formula that we used in the previous section for arc length. I'm just changing the variable so that we can have an upper limit that is a variable. Okay, now this written another way, which is 0 to t of the magnitude of v prime of u, which is just the speed. So from that, what we want to do is we want to take the derivative of both sides. And I'm going to differentiate with respect to t. So the derivative of the left side, the derivative of s with respect to t, will be the derivative of the right side with respect to t. Now, if you remember the fundamental theorem of calculus, the part we don't use very often, says if you take the derivative of an integral from some value a to the variable t, that is just the same thing as that integrand evaluated at the t. So this would be the magnitude of v prime of t, which is just the speed. So what this says is that the derivative of the arc length with respect to time is the speed. So the change in the arc length with respect to time is just the speed of the curve. So if we want to figure out a function for the arc length in terms of the parameter t, we're determining our speed. So this is the formula that we're going to use if we want to find that function for the arc length. Now notice here, if we did this from, if we had that the speed was 1, then we would be integrating s of t equal from a, let's see, whatever the value of a is to t of 1 would end up being just t minus a, which is just, it would be the arc length if the speed is 1. So what this says is if the speed's 1, the arc length is just that parameter t. So now let's find the arc length function. We're given the helix r of t equal to 2 cosine t, 2 sine t, 4t, and we want the arc length. The arc length, s of t, is given by the integral from a to t, which the a value starts at 0, times of the magnitude of v of t. I think I used v prime before. It's v of t or r prime of t, except we need u. Okay, so let's find v of u, which is r prime. So first, v of t is r prime of t, which is negative 2 sine of t, 2 cosine of t, 4. So v of u will be negative 2 sine of u, 2 cosine of u, 4. So we're integrating from 0 to the variable t. The magnitude of v of u will be the square root of negative 2 sine of u squared plus 2 cosine of u squared plus 4 squared. Factoring 4 from the first two terms, we get sine squared plus cosine squared, which we know is just 1. And now we have a formula for the arc length in terms of the variable t. The arc length is just 2 times the square root of 5t. Now let's find another description of the helix that uses the arc length as the parameter. We see that the arc length is not the parameter t in this case. It's 2 times the square root of 5 times t. So how do we get a description where the arc length is the parameter? It's really very simple. we'll take the formula that we just got. We know that S is 2 times the square root of 5t. That means that t would be S divided by 2 times the square root of 5. So in the description given above, on this right side, I'll change all the t's to S divided by 2 times the square root of 5. So I'll have 2 times cosine of S divided by 2 times the square root of 5 to sine of S over 2 times the square root of 5, 4 times S over 2 times the square root of 5. And now if this description was good for t greater than or equal to 0, that's equivalent to S being greater than or equal to 0. And now our new parameter, our new variable in this description is actually S. So this will be R of S. And simplifying, not much you can do here. Try to distinguish between your S's and your 5s. And that's our description of the same exact curve, same helix, except now the variable S is the actual arc length that's been traveled. So when S is equal to 3, the length of the curve that's been traced will be 3. It's the same as the arc length.